While Mike is booting up, I'll tell you that another part of our issue is to achieve these high I/O ops very cheaply. If you go around and look at Fusion I/O and what's this, Texas, I can see them from here, RAMSAN, Texas Memory, RAMSAN. Lots of people are looking at how to do fast I/O ops with Flash. We have data to show you that this approach that we're using with the Intel's flash drives is among the cheapest. If you, a very interesting metric of merit is I/O ops per dollar. So if you want to, if you want to look at some of that data, that's really the argument for the data challenge is how many I/O ops can you generate per dollar, and this seems to be a very economical way of doing that.
So Allan was talking about the prototype system that we have running now at SDSC called Dash. I want to return to the new system that we'll deploy in 2011 called Gordon. And the basic element of Gordon is what we call a supernode, and that is illustrated here. A supernode is composed of 32 APRO xtreme-x compute nodes, and these will be dual processor Intel Sandy Bridge nodes that will deliver at least 240 gigaflops per compute node, and each have 64 gigabytes of RAM. So that's the 32 yellow boxes that you see here. And then to that, we add 2 I/O nodes that are similar to what Allan described, but somewhat more powerful. These will have Intel SSD drives. Each I/O node will have 4 terabytes of flash, so a total of 8 terabytes on one supernode. And each I/O node would support 500,000 I/O ops. And then tying all of this together is the ScaleMP VSMP software, which virtualizes the memory within the supernode. So you put all of that together, you have a supernode with 2 terabytes of RAM and 8 terabytes of flash, 10 terabytes total storage per supernode. And that's a number that we tried to hit because 10 terabytes is, when you ask application scientists, how big are your databases now and how big will they be in a couple of years? 10 terabytes is the sweet spot. So that was the supernode, and now Gordon is 32 of these supernodes hooked together via a scalable interconnect shown here. So 32 supernodes, 32 nodes per supernode. That's 1024 compute nodes connected together by this 3D torus interconnect, which is based on dual rail QDR InfiniBand. And then, of course, we can't do without disk storage, and so we'll put 4 petabytes of disk storage on Gordon that would be connected in a way to sustain more than 100 gigabytes a second. So this chart here just racks and stacks the aggregate capabilities of Gordon. Total speed, 245 teraflops, quarter of a petaflop. Not the fastest supercomputer in the world, but the analysis is, you know, sort of, well, the flops are just a means to an end. It's getting the data in and out to analyze that is really the emphasis of this system. 64 terabytes of RAM, a quarter of a petabyte of flash, altogether 320 terabytes of storage for applications. This is an interesting number. The ratio of the total storage to the speed of the system, most HPC systems, this number is a tenth or less. For this system, it's 1.31. So it's a very byte-intensive system. The total I/O rate to the SSDs is 35 million I/O ops. And if they do start a top 500 for I/O, random I/O, perhaps we'll be #1 when this system is deployed. The network has a bidirectional bandwidth of 16 gigabytes a second, network latency of 1 microsecond, 4 petabytes of disk storage, as I said. So what I'd like to do now, toward the end of the talk, is talk briefly about the applications that we envision running on Gordon. And we basically did an analysis of what's out there and discovered that they fall within 2 principal classes. One we call data-intensive predictive science. These are nothing more than traditional HPC applications that have extremely large working sets in RAM or on disk, simulations that generate a lot of data or simulations that read in a lot of data. And then the second class is, we just put it under the rubric data mining. This is where the data would come from somewhere else, come from the real world, for example, from measurements, and it would be terabytes in size, and you want to comb through it to look for patterns and correlations. Now, the interesting thing is these two classes are not independent. If you have a very large HPC application that generates lots of data, when you're done with the simulation, now you've got to do the data mining to figure out what you computed. And so we think that the fact that there are many systems out there that do a good job on generating the data, but not a very good job on analyzing the data. And so we see Gordon as filling that niche. So I've got a few slides here with more details. Data mining applications will benefit from Gordon in the following way. One that you can imagine is genome sequencing, where you have these sequencing machines that do shotgun sequencing and give you very short segments of DNA that then have to be put together into a global sequence. That's a very data-intensive operation because you basically have to create an index table to bring the little pieces together into the full sequence. That's best done in a large shared memory environment, which Gordon will provide. Astronomical surveys are also collecting data on hundreds of millions of galaxies that would go into a database, a relational database for scientific queries. This is really what Allan was talking about with regard to DASH. And holding those databases will require a machine like Gordon. What's very exciting, and I would say that this is really future stuff, is having enough flash memory to host multiple databases of different types and allow cross-correlations between them. So we imagine that you'll have perhaps several supernodes, and within each supernode a different kind of database, and those would be available to the analyst for querying both separately and together. And that's called federation of database. And we're seeing need for that in drug discovery, social science, biology, epidemiology. This slide goes into that in a little more detail. There is something called Metcalfe's law, which says that the possibility of new discoveries grows quadratically with the number of federated databases. And so here is a very complicated slide from health sciences where you could imagine having a clinical database, a genomics database, a structural database, and correlating all of these together to understand the efficacy of new drugs. This would be supported by Gordon. Interaction network analysis. You may have seen these kinds of network trees that come from an analysis of social networks. It's interesting to study how various nodes interact with other nodes. This is also at the heart of a lot of Homeland Security work, by the way. It looks the same. And the idea is to be able to hold the entire graph in memory. And there, the virtual shared memory on Gordon will be indispensable. In the predictive sciences area, we have some familiar applications from the geosciences, oceanographic or atmospheric sciences. And there, what they do is not just simulate, but they do what is called an inverse problem, where they're trying to do a state estimation on the ocean or the atmosphere. And I have a slide, the next slide goes into that in a little more detail, but this will benefit from the balance that we've built into Gordon, especially the large RAM per core and the fast I/O rates. And then finally, there is a class of HPC application that you will not see running on the petascale systems because they simply do not scale. These are quantum chemistry codes, structural engineering codes that have very large working sets, but the algorithm itself does not scale to many thousands of cores. And so this will be a place where those kinds of applications can be executed. I just want to say a few things about this geophysical application, which is, of course, becoming more and more important with global climate change. We're all familiar with putting the equations of motion into a supercomputer and running a simulation like we saw the previous speaker talk about. That's kind of easy. What's hard is going out and measuring through buoys or other probes the state of an ocean, and you have a small number of these sampling points, and you want to fill in the rest. You want to construct a 3D plus time field from sparsely sampled data. How is this done? The way this is done is the data from the sampling points gets fed into the simulation. The simulation runs forward, and then you run a different kind of simulation backward in time. So here's the forward simulation, putting in the measured data here. What is then done is to run a different kind of calculation called an adjoint sweep that goes backwards in time. Well, how do you go backwards in time? Well, you have to read the data that was dumped by the running simulation as it was going forward in time. And ideally, that simulation would have dumped every time step. And you can imagine the data requirements if you did that. Well, they don't have enough storage for that. So what they do is they do it in a hierarchical way. Instead of running like this, they'll run for a piece, and then they'll run for another piece and another piece. And they store all of this intermediate data on disk at present. With Gordon, they'll be able to write this data into Flash and have much higher throughput as a result. This slide here is just amplifying on the modestly scalable codes with large memory needs. Gaussian is a very commonly used quantum chemistry code that scales poorly but has very large basis sets. Abacus structural engineering codes. These are just difficult to parallelize because of the nature of the mathematics. And so APRO, I believe, does a good business selling to engineering firms or chemistry houses that use the large shared memory that come from the scale MP aggregation. So in summary, Gordon will accelerate development in a number of fields. It will enable new capabilities for data-intensive applications. And this will be in a broad spectrum of applications, some very familiar, others not so familiar. The people in the social science and the biomedical basically have stayed away from supercomputing because the architectures have not been a good fit for their applications. This will be done through a combination of large shared memory coming through the VSMP, balanced architecture that minimizes the bottlenecks, and then finally the fast I/O to flash, which we think serves a missing link in the memory hierarchy of modern systems. And with that, I'll stop and take any questions you might have.